let's welcome the last speaker for today. It's Oliver Bründler. He's a dedicated FPGA engineer with over 15 years of experience at Enclustra and PSI. He's also a regular instructor in FPGA design, and he's the maintainer of the open source library OpenLogic that you may remember from last year's FDF. And today he will show us how to correctly combine OpenLogic building blocks. Thank you.
Hello, can you hear me? Good. Welcome from my side. Today's presentation will be about some basic building blocks in OpenLogic and how you can combine them. I decided to take this as a presentation topic for this year's presentations because I got many questions from users in that area. My name is Oliver. I'm the maintainer of OpenLogic. Hopefully you know the library already, otherwise you get to know it now. What is on the agenda today, we will first talk quickly about what OpenLogic is, then we dive through the three types of components I present, FIFOs, with converters, and CDCs. There is more in OpenLogic, but the slot is short, right? And then we're going to quickly cover how you can combine those. First about OpenLogic, what's the aim behind the library? The aim is to have something like standard lib in C, C++, just for HDL, so that you don't have to reinvent the wheel all the times. It provides reusable basic elements like clock domain crossing, FIFO, with converters, delay lines, content addressable memories, stuff like that. Standard interfaces like SPI, I2C, AXI, and fixed point mathematics. At the moment, more to be come in future, of course. It's not open source. It's not providing you a full Ethernet stack or the likes. It's providing you the basic elements that you can use to build your code. So again, if you come to the software analogy, it's not an open source application. It's an open source library you can build your application upon. And what makes it special, or what is important to me, and then I try to focus on, is quality, good documentation, so it's really usable in the end. Proper continuous integration, so everything in there is regularly simulated, is regularly compiled with all the different tools, that all the code is vendor and device independent, and that it's usable from VHDL and System Verilog, and that this also is tested. It's free and open source. Well, almost free if you decide to donate something like $5 a month or so. It could help the project. You can also, of course, just use it free, but I'm very happy if you take the almost free road. Before we dive in, the slot is very short, so we're going to go fast. The presentation is about very high level, what is there, how you combine it, and not about how it's built internally. If you are interested in that, refer to the documentation. As stated, there is good documentation, so you can dive in yourself if you want to know about the details. Good. We start with FIFOs. That's the synchronous FIFO in OpenLogic, and that's just the entity declaration, right? And that might seem a bit daunting. Many ports, many generics, it's just a FIFO. I just want a FIFO. What you need to know in OpenLogic, everything comes with default values. All the generics and all the ports that are optional have default values. So whatever you don't use, what you don't care about, you just don't state it. It has a same default value. And I take care that they don't change all the time and mess up your design. If I change default values, this is a major version number increase. So you can be sure if only the minor number counts, you are safe even if you rely on default values. And you see, despite the entity declaration over here is quite large, you can instantiate it as simple as you can imagine a FIFO with depth, clock reset, input data, output data, and the valid and the read-ready signal. So everywhere, if you see a big component, don't be afraid. Very often, you can instantiate it very easily. What I want to talk about for the synchronous FIFO, because I got questions and I want to explain it, is how the levels work. The FIFO has a certain latency, right? And you have an input and an output level. They are thought in the way that the input level reflects what you write in. If you write a word in the next clock cycle, the input level increases. On the output side, this happens, or the out level increases 1 clock cycle later. If you read on the next clock cycle, this is reflected on the out level, and in the input level, it's reflected later. So whenever you are sitting on the input side and you are taking care about how much data is in there and is the FIFO full, also the full flag is based on that, you look at the input level, and the same for the output level output side. Then we have an asynchronous FIFO, of course, that looks very much the same as the sync FIFO, just that it has 2 clock domains, of course, and it has all the status signals duplicated in the 2 clock domains for obvious reasons. And there is exactly one generic which is different at optimization. You can optimize for speed or latency. That's a bit special for the asynchronous FIFO. Otherwise, it's exactly the same as the sync FIFO. So once you understood one, you can also use the other one. The thing that is cool about FIFOs is that we have a packet FIFO. That's a store and forward FIFO that allows you to repeat packet, to drop packets, even if you already started putting them into the FIFO, and also to skip packets. It's also very handy if you write protocol engines because it lets you know how many packets are there in the FIFO waiting for you to read them, so complete packets. And it gives you the size of the packet on the output side. If you assemble an Ethernet frame, you need to know how the packet is, how big the packet is on the first word. The packet FIFO from OpenLogic is designed for exactly such purposes. And of course, as you know, if we have to drop packets while we are writing them, we can only send them to the output once the last word is in. So it's a store and forward FIFO only after the yellow packet here was fully written and the last word is in, the packet goes to the output, right? So you get a latency of 1 packet by the nature of a packet FIFO. You can drop packets, so even if you already started writing data, and even if you write more data, you can signal that you want to drop this packet, and then, as you can see here, the yellow packet doesn't show up on the output. You can skip packets. We see here a packet that has a size of 4 words, and after 3 we say, yeah, I'm not going to use that packet, I drop it. I skip it, and then you don't get more data out of it, and you get the next packet immediately. And you can also repeat packets, so if in the middle of a packet you feel like, oh, I need that packet again, probably something went wrong, I need to repeat it, I need to retransmit it, you can signal this, and you get another copy of exactly the same packet. As said, very useful for protocol engines, retransmission and the likes. Now about width converters. For the width converters, we have also 3 types, an integer downsize, integer upsize, and arbitrary width converter. The integer downsize takes something like, for example, 8 bits in and then makes 2 times 4 bits out of it. It also comes with proper word enables. It's not byte enables because sometimes you have widths like 7-bit or 4-bit or whatever. But if you have 8-bit to 4-bit converter with the smaller word is 4 bits, you have those word enables. So if you send in the last word and say like, yeah, I only want to have the lower nibble here, the D represented, on the output you get the last word of the packet shown only the D. So it also works with unaligned packets. The very same for the integer upsize, of course. Works the same way, has word enables, can handle unaligned packets. The coolest one of the width converters is the arbitrary width converter, where you can do anything. Very often you have something like 24 bits for an RGB pixel you want to send through a 16-bit link or something like that. That's handled by the arbitrary width converter. The example here shows 8 to 7-bit conversion. Think of, for example, a byte stream you want to send through LVDS serialization with 7 bits. You just take the OpenLogic component, you send the data in, and it will be width converted automatically. So you get the bits sorted in 7-bit chunks. Of course, at some point, if you convert from 7-bit to 8-bit, at some point you have a bandwidth problem, right? You only send 7 bits every clock cycle out. You get 8 bits every clock cycle in. As everywhere in OpenLogic, we have AXI stream handshaking, ready valid. Same here. When there is the moment where you need to wait for a clock cycle to push in more data, it will just deassert the ready, and you can connect whatever component with AXI stream handshaking. And the very same arbitrary width conversion you can also use in the other direction, of course. For example, for 7 to 8-bit, same game. Just there you have the gaps in the data on the output side, and yeah, the valid goes low for a clock cycle once there is a gap in the data. Good. Now about clock domain crossings. That's always a hot topic. It's actually one of the bigger values in OpenLogic I see, because many people design their clock domain crossings, and very often they are in the end not working or not reliably working. We all know the basic of a clock crossing, right? We have a double stage synchronizer over here. In OpenLogic, we also have the flip-flop on the source clock domain included. So that's there to avoid that users could inject any logic here, which wouldn't be a good idea. That's the basis for all clock crossings. So in OpenLogic, we have, I think, 8 to 10 or the likes different clock crossings, and all of them use this one clock crossing for individual bits. And this also means that whatever we do here, we can reuse everywhere. It comes with scoped constraints for Vivado. So if you have that clock crossing in your project, Vivado automatically does the timing constraints for it. If you are not using Vivado, you can manually constrain it, but always with the same constraint, max delay for the faster clock period. The number of sync stages over here you can configure. So you can reach higher MTBFs if you want. And this then applies to really all the clock crossings. They will give you the number of sync stages configurable. The next clock crossing that is a bit special to OpenLogic is the reset clock crossing. We all know the typical reset synchronizer. That one goes a bit beyond. It makes sure that both sides, both clock domains, are in reset for at least one clock cycle at the same time. This avoids problem where one side comes out of the reset and starts working, and the other side is resetted later, and they don't understand each other. So in OpenLogic, whenever we have clock crossings, we use that reset clock crossing. You can also use it as a user, of course. And that makes sure that really both sides go to reset first and are then released, and it's not one side continues working and the other comes already out of reset and stuff like that. You see here reset request, and then both sides go into reset and are then coming out of reset one after the other. If you use clock crossings from OpenLogic, you see reset outputs sometimes. Wherever internally such a reset clock domain crossing is used, I also provide the output, so you can reset your corresponding domains in the user logic, but you can also just leave those ports open if you don't care. Good. That's the full list of clock crossings and what they can do. I won't go through each and every cell in here. If you are interested in clock domain crossings inside OpenLogic, just go to the YouTube channel. There is an OpenLogic YouTube channel. I have a video about clock domain crossings where I describe the inner workings of all of them and the likes. So you are welcome to go there for details, but the overview here is very good to see which clock domain crossing fits my application. There is only a few things I want to quickly say. There are, besides all the other clock crossings that are for arbitrary clocks, there are clock domain crossings for phase-aligned clocks. So, for example, if you go from 120 to 240 megahertz from the same PLL, you can use those, and they are super efficient. And there is a note about the handshaked and async clock crossing. They both look the same. They both have full AXI stream handshaking with ready and valid on the input and on the output side. It might seem like a FIFO is more resource consuming than simple handshake FIFO. If you are on technologies that have distributed RAM, which nowadays is almost every technology, very often an async FIFO, a small one that fits into distributed RAM, is much more resource efficient than a handshaking. So if you are on, for example, AMD devices, just stick to the async FIFO and don't use the handshake FIFO, the handshake clock crossing, because it doesn't really have advantages. Use it when you don't have distributed memory, because you are on a, I think, lattice ICE devices and the likes don't have. So decide wisely here. For the others, we can quickly go through what they are. The individual bit clock crossing, we checked. That's a double-stage synchronizer. Reset clock crossing, we also looked at. There is also clock crossing for pulses. Simple one for low-rate signals with a valid data bus plus a valid signal. And a status clock crossing. The advantage of that one is that it doesn't know anything about when signals are valid. It doesn't know anything about what's the ratio between the clocks. It just makes sure that every now and then a consistent set of the bits is moved from one clock domain to the other. It's very useful to observe counters or the likes if you don't know at what clock rate the register bank runs, and the internal clock might be faster or slower, then it's very useful. Good. Now, how do you combine them? That's the main topic of the talk, actually. I got such questions like, where is the asymmetric FIFO in open logic? There is none. You just combine things. You take a width converter and you put the FIFO after, for example. That one is optimized for throughput because it's burst capable on the output. But you as a user could decide that you want to save memory instead of having throughput, right? If you do it that way, you have a very wide FIFO here, and you consume 4 block RAMs. If you are actually not interested in throughput, you can just switch to things, have a very small FIFO and the width converter after, and suddenly you have only 1 block RAM. So it's somewhat dependent on what you as a user want. That's why I didn't build an asymmetric FIFO that just takes an assumption what you want, or provide, I don't know, 20 different components with different flavors that users have problems with understanding. It's better to have simple, easy things, and you play Lego and assemble them the way you need them. If you want an asymmetric FIFO or if you want the same width converter with an asymmetric FIFO, you cannot just use an async FIFO here. I got the question, where is the double width half clock converter? Well, you can build it also with a width converter and the clock crossing. Here we would use a synchronous one, of course. You could also go asynchronous here and use an asynchronous FIFO instead of the synchronous clock crossing, right? So it depends on you, on what your application needs. Where is the gearbox? Was also a question. You use the arbitrary width converter and an asynchronous or synchronous clock crossing, depending on which one. So it's always, if you look for something that you miss very often, it's 2 or 3 components to combine, and it gives you the freedom to combine them in the way that makes most sense for your application. So the general approach is that OpenLogic provides you the basic elements, and you combine them as needed. If you miss something, first check whether you can make it happen by combining. If you don't find a way, just drop me a note, make an issue, I will come back to you. The cool thing about that is that we have a very limited number of entities that are easy to understand, and that you as a user have the flexibility to optimize things by assembling things the way you need it for your application, and not the way I thought probably most users need it. The downside is you're going to use your brain. Well, in the ages of AI, you probably are happy to. Yeah, what's next for you? Go and use OpenLogic, get it from GitHub, get it through ViewSock, it's integrated there. Inform yourself, documentation is on GitHub. There is a YouTube channel with not too many videos, but one specifically about clock crossings, which probably is interesting to watch. Then help me spreading the word. Inform your friends about OpenLogic. Post on whatever socials, repost my posts. Then, of course, contribute. You can contribute code. I'm very happy to get contributions, but you can also contribute by just writing me that there is a bug somewhere, there is a problem in the documentation, you don't understand something. This gives me the chance of improving. Then, as said, I'm very happy about every $5 a month. If you want to make that happen, to help me cover tool costs and the likes, just go to GitHub, press the sponsors button. You can pay by credit card and donate me your $5 a month to help getting the project running and cover the costs. And of course, give it a star on GitHub. That helps a bit with visibility. What's coming next in OpenLogic? I'm currently working on DSP elements. Next things there will be FIR filters, NCOs, and approximations. That's currently the hot focus. Another thing that's ongoing is fault tolerance. Could be interesting at CERN. ECC-protected data streams, ECC-protected RAMs, and FIFOs. And I want to say thank you also to many maintainers that have open source tools that help making things like OpenLogic happen. This is vUnit for simulations or for the setup of simulations, GHDL and NVC as the simulators, VSG as the linter I'm going to use, and Wavedrum as the tool I use for actually good documentation on all the waveforms. That's it from my side.
Thank you very much, Oliver, for a clear presentation. Your last questions?
Hi, I have a question about the license. Yesterday today, Javier has presented about the open source CERN hardware license. Have you ever considered applying this license for the OpenLogic library?
Yes, I have. The license situation in OpenLogic is as follows. Some of the code is based on what I open sourced at PSI some years back. Under the PSI HDL license, which is an LGPL license with a few additional lines covering explicitly FPGA use, allowing to ship bit streams and the like, just because there is a static linking clause in LGPL, which is problematic. So it's, from the content, it's fine to use. It means, in the end, if you modify something in the existing OpenLogic code, you have to open source it. But if you just use the library, there is no copy left to your project, and you can ship binaries and hardware the way you want. I am in contact with PSI to discuss license topics. One is whether we can switch to the CERN license, because it would be the better license for such a project, right? The other topic is also dual licensing. There are people that do want a license that allows internal modifications, and they better want to give a bit of money, which would help funding the project. So I am in contact with PSI on that license topic. Currently, the last feedback I got was positive, but I didn't get feedback for the last few months. I'm pushing forward, but it's somewhat slow from the other end. Currently, it's the PSI HDL license, which is built on LGPL, because taking over some code forced me to. But hopefully, in near future, we're going to change that.
Thank you.
Thank you once again for maintaining the library. I just have one question on your slide 26 about the reset. How do you propose to use this? So reset synchronized to destination clock domain, yes, but like again in the source clock domain reset, how do you how to use it? So the reset out in the source clock domain.
So I didn't get the question.
The reset is generated and synchronized in the destination clock domain. So I can use that, but like the reset which is output in the source clock domain itself, what's the logic?
If you have logic, let's say you have, the very simplest example is a pulse clock crossing. On the source clock domain, you toggle a signal, and then you synchronize it on the destination domain, and you look for edges. And the problem is if the clock frequencies are far off, one clock is 50 megahertz and the other one is 500. It can happen that you reset one of the sites. Let's say you reset the source clock domain, then your toggle flip-flop gets reset, and then the destination clock domain sees like, oh, I got an edge here, and your logic reacts to the edge, and you actually never ever have an edge. Something bad might happen. What we do here is we make sure that both sides go into reset on the next clock edge they have, and really after that they come up, so you know that they both come up in their reset state. So it's in such cases where you need it. And whenever you have a clock crossing that has the reset clock crossing in, you get that reset output ports. You can, or where you get the merged reset, right? If you are on the source clock domain and you have that reset output, it could be that you don't have a reset on your side, but on the destination clock domain, somebody pulls the reset. You get that out on the source clock domain, so you know, okay, somebody on the other end reset it. Probably I'm not sending him the other half of the packet because then it starts in the middle or something like that.
So then basically in both the sides, for the as a reset input, it should be the reset out used, yes. Not the reset
I mean, both sides can use reset out. You always have to have a clear concept of who is the master here, right? It's like, for the logic close to the clock crossing, usually it makes sense to reset both sides, but you also, not in all cases, want to reset the full clock domain. It depends a bit on what you are doing, right? The functionality is there. You can use it or you can omit it.
Thank you.
Please go ahead.
Hi. Do the compilers have any issues with these in terms of timing violations? Are there special constraints needed that come along with the cores, or do the compilers think, oh, this guy knows how to program, it's good?
I didn't get it acoustically. Could you repeat? It was about the constraints of the...
Yeah, so if I put something like on screen right now, if I put it all over my code, will the compiler in general be happier? Or do I need to add extra constraints for these kinds of components?
What toolchain are you using?
Altera mostly.
Okay. Because in Vivado, it's super simple. You just drop in the open logic. There is an import script for importing it into Quartus, Vivado, whatever other toolchain supported. And if you use that script in Vivado, the auto-constraining comes with it, and you don't even have to care about clock crossings. You just get the constraints. You don't have to care about the constraints. If you have a clock crossing in, it's automatically constrained. If you work on Altera, in the end, you just, for every clock crossing, need to do that max delay for the faster of the two clocks, and you are good. Now, there are different ways to do that. You can just basically write from any clock in my design to any other, the shorter of the clock period. That's a very short list of constraints, and you are done super fast. But it doesn't prevent you from having uncovered paths. Or you can go a bit more into detail and say, like, okay, here I have a clock crossing, here I want to apply this constraint, and over there I want, but I say it once per clock crossing. So that depends a bit on you, whether you want to be specific on wherever you are sure you have a proper clock crossing, or whether you want to be generic and say, like, yeah, I'm sure everywhere I used one. But it's always the same constraint, so it's easy to apply.
Okay, thank you.
Thank you for your presentation. For modules such as FIFOs and width converters, have you made a comparison between your implementation and some IPs that are already present in AMDs. So even AMD's IP library has data FIFOs and data converters, AXI broadcasters, combiners, etc. Like, so, like, have you made a comparison in terms of logic resources?
Some I did. I did not spend years on it. I know that the synchronous FIFO, for example, is a bit bigger, the open logic one. Okay. It costs you few LUTs more. Okay. What you get is portability, but if you want to be very efficient, potentially, if you count kind of tens of LUTs and not hundreds, then it could matter. One specific thing to mention is if you are in the situation where you count individual LUTs or tens of LUTs, you potentially want to use the built-in FIFOs that are in the block RAM integrated, right? That don't use any LUTs. Of course, that's kind of portable open source code is nowhere close to that specific implementation where you don't need any LUTs. Generally, if you compare it, it's not far away. Okay. But there is a trade-off you make with portability versus the absolute maximum optimization.
Yeah, okay, thank you. Thank you.
Thank you so much, Oliver. We made it in time.